So, as continuation of the latest topic, we'll move on to the different Atterberg limits and consistency indices. So, what are those? What are these? Atterberg limits and consistency indices. The presence of water in fine-grained soils can significantly affect associated engineering behavior, so we need a reference index to clarify the effects. The reason will be discussed later in the topic of clay minerals. We have these different limiting state, of the soil. For example, this figure or graph here in the upper portion, I mean this one. We have the water content. You will base on your evaluation. Now, based on the water content, we have the 0 to how many percent, or to 1. So we say brittle solid if the liquidity index, actually the liquidity index is also the water content of the soil. So if the water content or the liquidity index of the soil is less than 0, meaning the clay or the soil is brittle solid. And SL, this is the shrinkage limit. Now, between the shrinkage limit and plastic limit, this is the semi solid. And in the plastic limit, your liquidity index is 0. So from this plastic limit to liquid limit, that is between 0 to 1, no? Your soil is in plastic solid state. Then if the liquidity index, in here, in the liquid limit state, your liquidity index is approximately equal to 1. And if the liquidity index is greater than 1, meaning your soil is in the liquid state, no? This is in percentage water content. Say we have 60% or 34%. So I don't know. And this is the representation of the stress versus strain, no? So as you can see in the first graph, if the water content is less than the plastic limit, so increasing the load, your strain or deformation is actually smaller, gamay lang. If the water content is less than the plastic limit. But if the water content is almost equal to the plastic limit or the liquid limit, in the plastic limit, this is the behavior. There is this peak portion and will eventually go down. And if the water content is almost equal to the liquid limit, this is the behavior of your soil when subjected to load. So you can see that increasing the stress or the loads will make that the strain will be bigger or dako ang iyahang deformation, And if the water content is greater than the liquid limit, so almost mahimo na siya as liquid, You can see that there is this behavior as horizontal. So bisan pag you will increase your load, or your stress, grabe ka, horizontal ang iyahang graph. Walay dili siya how to say, maka-resist og loads, no, or forces walay kusog because it is already in liquid state, no, and the deformation is greater. So this is the continuation of um, the Atterberg limits, no, of the, I mean, different state of the soil. So from dry soil, if you increase the water content, then the soil will be the fluid soil water mixture na siya. So in here, from the solid state of the soil, so the limit state of that between the semi-solid and the solid state is the shrinkage limit. So shrinkage limit is a state at which if the soil will lose its water, shrink siya, di ba? There is this stop a change of volume. So from semi-solid to plastic state, the boundary, is the plastic limit, and from the plastic limit to liquid state, the boundary is the liquid limit, no, state of the soil. We have this different method to determine the liquid limit of the soil. We have the Casagrande method and the cone penetrometer method. So the Casagrande is based on the ASTM, or the American Society of Testing Materials, D4318-95A. So Professor Casagrande standardized the test and developed the liquid limit device. So it produces, or the output is, a multi-point test. So you can have many points to determine the liquid limit of the soil, or you can have the 1-point test. So on the 1 point, then you can obtain the liquid limit of the soil. For the cone penetrometer method, this method is developed, this BS13, or the British Standard 1377, Part 219904.3. This method is developed by the Transport and Road Research Laboratory in UK. There is also multi-point test and a 1-point test. And a continuation for the determination of liquid limit, you can have this dynamic shear test, which is the shear strength is about 1.7 to 2.0 kPa, and the pore water suction is about 6.0 kPa from Head 1992 and Mitchell 1993. Also, these are the methods now to determine the liquid limit of the soil. You can have also particle sizes and water. So passing number 40 sieve and or 0.425 millimeter, and using the deionized water, the type and amount of cations can significantly affect the measured results. But the most commonly used method are these two methods, no, Casagrande and cone penetrometer method. In the engineering, the available method is, before, no, in the laboratory is the Casagrande method. I hope, no, you did that one in your laboratory. We did this one, no, during the undergrad, this Casagrande method. And the cone penetrometer method, I think this is the new, there are new equipment now in the IEL, engineering, integrated engineering laboratory. So ano siya, I think this is the Casagrande method, no. This is the device. You have this pan, what is this, pan, and the metal, no, the end, magkuan ka og 25 blows, no, iana siya nimo. This is the actually the controller, no, kani siya. Hindi ka mag-control sa imong 25 blows. Then the closing distance is 12.7 millimeter or 0.5 inch in here ni kanino closing distance of the soil. So kani siya, butangan nimo ni siya soil, imong this ingani no, and after 25 blows you get the soil and oven dry, get the water content of that soil. Try to search now. I think you already did this one in your laboratory since this subject is only lecture. So I presume that you finish already your laboratory subject for this engineering, geotechnical engineering 1. This is the multi-point now method of the Casagrande. You can have at several number of blows. Now this is the moisture content versus the number of blows in log scale, no? And if try to trace that one, this will be, or line will follow the straight line. Now this the flow curve. So multi-point method, so there are several methods, and the flow index, this is the flow index is the meaning of that flow index. It is a right. Yes, the flow of the slope, the flow line, no. All right. Okay, this is also a determination of uh, one of the indicator, no, of your of the value of your liquid limit. So you can obtain the flow index using this formula, no, the what moisture content 1 for example, moisture content at blow 25 blows, no, what is the moisture content? You have to try to see in this flow curve, no. Then at N2, or for example 30 blows, no, project the 30 blows, then what is the moisture content, then you can determine the flow index. Choose the positive value. Then the water content of the soil is equal to negative of the flow index log number of blows plus constant. Okay, so this is the 1 point, no, method, 1 point method of the Casagrande. Right. So this is actually the equation of the flow line, but this flow index is actually not so applicable. An indicator of the state of the soil. So mostly ang kasagara state sa soil are the liquid limit, the plastic limit plasticity index, no? Let's move on to the 1-point method of the Casagrande. So in the 1-point method, you have to just choose, no, a 1 point, no, assume a constant slope of the flow curve. Then the slope is a statistical result of the 767 liquid limit test. Then using the 1-point method, you can get the liquid limit through this formula. It's equal to the W sub n. This is the corresponding moisture content at a specific number of blows. Now, for example, you have already established a curve. Then at 25 blows, what is the moisture content? No, if you project the 25 blows, project mo diha, what is the moisture content? Then applying this 1-point method, then you can determine the liquid limit. The tangent beta is proposed to be 0.121, but the beta is an empirical coefficient, so it is not always 0.121, depende sa soil, no? Sa properties sa soil. The good results can be obtained only for the blow number around 20 to 30. That is why it is proposed for the Casagrande method that the number of blows is 25 blows. No? For the cone penetrometer method, this method is developed by the Transport and Road Research Laboratory. So, this is the device now. Alright. For the cone penetrometer method, in this test, the liquid limit is defined as the moisture content at which a standard cone of apex angle of 30 degrees and weight of 0.78 Newton will penetrate a distance d equals 20 mm in 5 seconds when allowed to drop from a position of point contact with the soil surface. So due to the difficulty in achieving the liquid limit from a single test, 4 or more tests can be conducted at various moisture contents to determine the full cone penetration at D, and a semi-logarithmic graph can be plotted with moisture content W versus cone penetration D. So actually, for the multi-point method, no, the cone, the penetration cone of cone in millimeter is in logarithmic in form, no, in this graph. So according to the DAS, no, this is from DAS. Actually nabali ni siya. This is the penetration D in millimeter, no? This is actually in logarithmic. So example, that is 10, 20, 40, 60, 80. Then nabali moisture content dapat diri. This is moisture content in percent. Say 30, 40, 50. And say this is the graph now. You have the multi-point. So at a specific number of blows or moisture content, not specific moisture content, what is the penetration at, say, at 20, no? For the multi-point method, the formula for the flow index IFC is equal to moisture content 2 in percent minus moisture content 1. I mean, you choose, no, you select different points or 2 points in the graph, then you can compute the flow index log the specific penetration of that moisture content 2 minus log penetration 1. So yan siya. But anyway, we're not, this is this kind of indicator, no, or parameter, rare ra kay siya nga gamiton in the problems, no, or even in the board exam. Then for example, this one is a 1-point method, an empirical relation. So we have this table, now suggested factors for cone penetrometer 1-point liquid test from Clayton and Jukes in 1978. So we have the different penetration in millimeter. Then we have the suggested factors, now if the soil is of high plasticity, of intermediate plasticity, and of low plasticity. For example, the penetration depth at 15. So for soil of intermediate plasticity, the factor is 1.094, no? And the moisture content of this soil is, say, 40%. So since the factor is 1.094, 40, 40 times 1.094 is equal to 44%. This is the liquid limit of the soil using the 1-point method, which is an empirical relation for the cone penetrometer, no, method. So the comparison between the liquid limit for the Casagrande test and for the cone test or cone penetrometer method is the good correlation between the two methods can be observed as the liquid limit is less than 100. So between here, kanisha actually, this is the good correlation if the liquid limit is less than 100. So meaning mo coincide ang duha ka method, the Casagrande method and the cone penetrometer method. So beyond this 100 LL, dili na there is inconsistency of the two methods, no? So kanila gud ang how to say, reliable, no? When the liquid limit is less than 100. So we have also the term plastic limit. So plastic limit, no, this is actually the soil and the ruler, no. The plastic limit is defined as the water content at which a soil thread with 3.2 millimeter diameter is 0.2 millimeter diameter just crumbles, no. Then plastic limit is kanang, the method for this one is soil, the oven dry, I mean sieve soil, no. You put water, then the soil will act as a plastic, no, soil. Then you have to drag in the kuan siya, kanang imo siyang kuan sa glass, no. Hantod mabot ang time nga mo crumble siya. So at that time nga crumbles ang soil, put this one sa oven dry, then get the moisture content. Then the moisture content, that is the plastic limit of the this soil. No? We have also the shrinkage limit. The definition of the shrinkage limit is the water content at which the soil volume ceases to change is defined as shrinkage limit. So we have this graph now. Shrinkage limit is actually this part here. This part here is ang soil ani is naa siya water. The time nga mawala no ang water, so at this point the soil will stop to change its volume, no? As you can see, nag-straight lang na siya diha. So this limit here, this is the shrinkage limit. The increase in the moisture content will be your plastic limit, then your liquid limit. For example, this one, now continuation of the shrinkage limit. You have the soil, no, of mass 1. This is before drying the soil. Then after obtaining the water, or after drying the soil, when you weigh the soil, so you have the initial volume of soil and the initial mass of soil, no? This is with water. Then after oven drying, we'll have the final volume of the soil and the final mass of the soil, so that the shrinkage limit is this formula. We have M1 minus M2 over M2 times 100 minus the initial volume minus final volume over the final mass times the density of water times 100. Now density of water, or 1000 kilogram per cubic meter, or 1 gram per cc. So the shrinkage limit, now although shrinkage limit was a popular classification test during the 1920s, it is subject to considerable uncertainty and thus is no longer commonly conducted. So one of the biggest problems with shrinkage limit test is that the amount of shrinkage depends not only on the grain size but also on the initial fabric of the soil. So the standard procedure is to start with the water content near the liquid limit. However, especially with sandy and silty clays, this often results in a shrinkage limit greater than the plastic limit, so which is meaningless, no? For sandy and for sandy and silty clays, no, which is meaningless because shrinkage limit is greater than the plastic limit, so meaningless yun siya, no? For sandy and silty clays, Casagrande suggests that the initial water content be slightly greater than plastic limit if possible, but admittedly it is difficult to avoid entrapping air bubbles. This is the disadvantage or drawbacks when using shrinkage limit as the one of the indicator for the classification of the soil. We have this typical values of the Atterberg limits. So we have the mineral, no, or this is different clays. Actually, this Montmorillonite, this is a very expansive soil. Meaning of expansive soil is kung observe siya water, grabe ang pag-expand, no, or pagdako sa iyahang volume. So this is very not good, no, not advisable for construction, this kind of clay. We have for this Montmorillon unit, the liquid limit is within this percent, now 100 to 900. Plastic limit is 50 to 100. The sinkage limit for this type of soil is 8.5 to 15, so on and so forth. No, these are the indices, no, that we discussed earlier, but to be able to solve now for the these different indices. So we have the plasticity index, or the PI, for describing the range of water content over which a soil was plastic. PI is equal to LL minus, or this is the liquid limit minus the plastic limit. No? For the liquidity index, or the LI, for scaling the natural water content of a soil sample to the limits, no? The Li is equal to the water content or moisture content of the soil minus the natural moisture content of the soil minus the plastic limit over the plasticity index. No? But the plasticity index is equal to liquid limit minus the plastic limit, so that the liquidity index is equal to the moisture content minus the plastic limit divided by LL minus PL. Now, we already discussed this figure here, no? This one. We have the classification, no, of the soil. So, if the Li is greater than 1, that is, the soil is in viscous liquid. If sheared, no? If sheared, meaning if subjected to loads or forces. And if the Li is within this range, 0 to 1, the soil is in plastic solid if sheared. And if the Li is less than 0, that is brittle fracture if subjected to forces or loads. So the failure, no, or fracture is brittle, meaning like the glass, no, mabuak siya because the Li is less than 0. So ang behavior ani tendency, this will act as the glass, or uga naman kay siya, no, less than 0. So gamay ra gid kayo ang ihang tubig. So that's why the failure or the fracture is brittle. We have also this sensitivity, no, for clays. Also a type of indices, no, or indicator, no, of the classification of the soil. Sensitivity for clays, no, this is only for clays, is equal to the strength of when its condition is undisturbed divided by the strength for a condition of if the condition is disturbed. No, the strength is actually the unconfined shear strength. So there is a device, no, or equipment to determine the unconfined shear strength of the soil. During the undisturbed, try to find or obtain the strength, and during during its disturbed state, then get the strength, then you can compute the sensitivity. So we have the typical values of sensitivity. We have the low sensitive, now for the range of sensitivity US and Sweden, no. Low sensitivity is 2 to 4, but for Sweden is less than 10. For medium sensitivity 4 to 8, but for Sweden is 10 to 30. And yes, this one is the clay particle and the water. So if the water content is greater than the liquid limit, so the soil will behave as like this one, no, liquid. Have also this activity. According to Skempton in 1953, the activity is equal to the plasticity index over the percent clay fraction by weight. Now, this clay fraction finer than 0.002 millimeter sieve. So, percent clay fraction nga finer aning 0.002 millimeter by weight. This is the value, no? Percent clay fraction. Then Pi divided by this percent clay fraction, this is your activity. So the purpose of this, both the type and amount of clay in soils will affect the Atterberg limits. So this index, this activity is aimed to separate the type and amount of clay in soils. Example of this one is for normal clays, the activity is 0.75 to 1.25. Now within this range, inactive clays is less than 0.75, and for active clays, activity is greater than 1.25. For high activity clay, large volume change when wetted, large shrinkage when dried, and very reactive in when it reacts now chemically. So for very high activity of type of clay, no, when added with water, tendency niya is grabe ang pagdako sa volume, pero pag remove pud sa water sa soil, grabe pud ang shrinkage, no? And very reactive when chemically react with other mineral or chemicals. So we have different activities of various clay minerals. So we have mineral and the activity. So the highest value of activity at for a specific mineral is, among this mineral is the smectites, no, which is the activity is 1 to 7, so on and so forth, is various clay minerals. For the engineering application of these Atterberg limits and classification indices, no, actually is the application of this one is for the next topic, which is soil classification, no. So for the soil classification, the Atterberg limit enable clay soils to be classified. So naa kay ranges of values. For example, kana siya nga soil is silty clay soil because the plastic limit is this value within this range. So ingana, no, this type of soil is very clay soil, ano siya. So the application of those different limits is actually for the soil classification. So this is the table, no. This one is table for classification of soil, this one, no. At later sa later topics, no, we'll discuss this one also. For example, this one is the liquid limit and the plasticity index. So for example, using the obtained values for liquid limit and plasticity index, then you try to trace this or project this in this graph. You can then determine the type of soil, if that soil is silty clays, clay silts and sands, low plastic or inorganic clays, sand and silty clays. So ingana siya, no. So later, no, we'll discuss this one also, later topics of this subject. So the Atterberg limits are usually correlated with some engineering properties such as permeability, compressibility, shear strength, and others. In general, clays with high plasticity have lower permeability and they are difficult to be compacted because the clays, no? The clays are actually ang iyang volume changeable ang volume labi nag-absorb siya og water munang difficult siya mo i-compact, no? And values for the shrinkage limit can be used as a criterion to assess and prevent the excessive cracking of clay liners in reservoir, embankment, or canal. So these are some of the engineering applications of this Atterberg limits, no? Values of the shrinkage limit is important, no? Criteria for assessing the excessive cracking because shrinkage limit is the limiting state for which ang clay or ang soil mo behave siya as kanang brittle, crack, or fracture, di ba? Remember in the previous slide? So, munang importante siya nga criterion in building, no? Reservoir, embankment, or canal. So, because, yes, embankment, no? For reservoir, kailangan siya imo siyang tambak, no? Tambakan imo siyang soil. Dapat ka na nga types of soil is you should have determined its shrinkage limit and those other Atterberg limits, no? So that you can assess and you can assess if that type of soil for embankment is good or not, no? For reservoir or canal. Then we have the soil structure and fabric. We should also, for this introductory part or beginning lesson of this course of this subject, we will also study the soil structure and fabric. Take note, the sizes of particles that make up a soil vary over a wide range. Soils are generally called gravel, sand, silt, or clay depending on the predominant size of particles within the soil. To describe soils by their particle size, several organizations have developed particle size classifications. So we have these microfabric features in natural soils. So, number one, we have elementary particle arrangement, so which consists of single forms of particle interaction at the level of individual clay, silt, or sand particles, or interaction between small groups of clay platelets or cloth, silt, and sand particles. So particle assemblages, which are units of particle organization having definable physical boundaries and a specific mechanical function. Particle assemblages consist of one or more forms of elementary particle arrangement or smaller particle assemblages. Pore spaces within and between elementary particles arrangement and particle assemblages. So we'll put this into figures or representation in the next slide. So we have the elementary particles of the soils. We have the individual clay platelet interaction. So this figure, and this is the individual silt or sand particle interaction, no, bigger in size, no, and the clay platelet group interaction. So this one, and the cloth silt or sand particle interactions, particle discernible. This is from the Holtz and Kovacs in 1980 and also McGowan in 1974. We'll now move on to the soil fabrics for granular soils. For granular meaning bigger, no, size soils. So we have this packing, no, this is the loose packing, which has voids in it, no, nasa mga voids, nasa mga gap, which is the voids for water and air, no? We have dense packing, which is compacted, no? Compact siya. And honeycomb fabric, so this one. So the honeycomb fabric is, how to say, metastable structure, and also a loose fabric will result to liquefaction and sand boil. This type of honeycomb fabric and loose packing are actually kind of arrangement of the soil na more likely to produce liquefaction and sand boil. So for the another particle shape, for the granular shape, no, of soil, we have these coarse grained soils, rounded, subrounded, the subangular, and the angular. Important for angular soils are angular soil particle means higher friction, and round soil particle lower friction. Note that clay particles are sheet-like. So more likely ang clay particles is a angular soil particles because it is not round, no? Alright, so this angular soil particle, no, especially for aggregates and rounded, no, as you've learned in your, or what you feel experience, no, naa siya'y different factor, no, because of its kanang friction, its tendency to bond with the concrete, with the, yes, with the concrete. So mas dako og bonding strength ang angular soil particle than the rounded soil particle. So we continue. This is the particle assemblages. This is the silt or sand. So these are the connectors, irregular aggregates, and the silt or sand particle, and the connectors, no? This from Collins and McGowan, and from Holtz and Kovacs. And these are, or this is the pore space types. Schematic representation of pore space types, meaning pore space types, this gap here, kaning gap diri sa soil particle are the pores. Diha mosulod ang air and water nga particle. So na siya pore space, no? Especially for water, no? This one, this gap or spaces are for water. If the soil particle will absorb no water, so diri sila mo sulod, pore space types. So this is the soil fabric for clay soils. So katong ganina is for granular soils. This time is for clay soils. So we have this terminology, the edge. This is the clay particle, and this one is the face, no? So disperse meaning no face-to-face association of clay particles. So disperse, no, bulag-bulag. We have aggregated face-to-face association, FF of several particles. So this representation, and flocculated edge-to-edge, EE or edge-to-face, EF association, that is flocculated, and deflocculated, no association between aggregates, no? And this is the representation, no, particle associations. We have dispersed and deflocculated. So this one. So dispersed, no, bulag-bulagin siya. Then deflocculated po siya. This letter B is aggregated but deflocculated. And this one is edge to face flocculated but dispersed. This association of particle is edge to edge flocculated but dispersed. Then edge to face flocculated and aggregated, this representation, and edge to edge flocculated and aggregated. So this one, and edge to face and edge to edge flocculated and aggregated. So this arrangement. So this actually, I think this one is found out ni nila through instrument microscope or anything that will expose the association of particles of clay, no? So basin sa instrument nga makahatag og ingon ani nga data or information. So microscope man na or those instrument, no, as advanced. For the summary, flocculated fabric are the edge to face EF positively charged edges and negatively charged surfaces. So this is the more common association of clay particles. Then edge to edge EE for aggregated fabric. So this two types, no, edge face to face FF and shifted face to face. For dispersed fabric, so this presentation, the net interparticle force between surfaces is repulsive. So dili sila ga attract na to each other. Fabric of natural clay soils. The individual clay particles seem to always be aggregated or flocculated together in submicroscopic fabric units called domains. So domains then in turn group together to form clusters, which are large enough to be seen with a visible light microscope. I see, microscope. Clusters group together to form PEDs and even groups of PEDs. So PEDs can be seen without a microscope, and they and other macrostructural features such as joints and fissures constitute the macrofabric system. So from domain to cluster then to PED, which can be seen through our eye siguro, no, okay, without microscope man. No. So using a microscope. Alright. So this is the fabric of the natural clay soils, domains and clusters with micropores. This one, enlargement, is this representation. Number one are the domain, then number two the cluster, and number three the PED, no? Number four the silt grain. 5 is the micropore, and 6 is the macropore, no? So macrostructure, including the stratigraphy of fine-grained soil deposits, has an important influence on soil behavior in engineering practice. Joints, fissures, silt and sand seams, root holes, valves, and other defects often control the engineering behavior of the entire soil's mass. The microstructure reflects the depositional history and environment of the deposit, its weathering history, both chemical and physical, and stress history. So this is the terms, no? Macrostructure and microstructure. Okay. So we'll continue, no, next meeting, maybe on Friday, for discussion on clay minerals and their significance. Right. This is more on chemistry. I think. Arrangement. Then we're done with this kuan. this part. Index soil properties. Alright. So I think that's all, and thank you for listening.